SANDHAN, All Gujarat Integrated Classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.
Hello everyone. This is Rajesh Khambolja from BA Engineering College, and next our topic today for mathematics is partial differential equations. So partial differential equations. So you have studied that the dependent variable is affected by only one independent variable x up to your 12th mathematics syllabus, right? So you have studied that generally y is denoted as a dependent variable on the independent variable x. Okay. So for example, y equal to x square, y equal to sin x, y equal to cos x, etc. So here, as x is the variable, and as we vary the value of variable x, we get the values of y, and we have graph of this function y is equal to f of x as the set of points x comma fx such that y equal to f of x. So in case of one independent variable, you have studied the calculus of one variable, that is limit of one variable, continuity of one variable, and then differentiation, that is derivative with respect to one variable. For example, age is equal to days alive per 365.25 days. So age depend on only one variable, that is number of days alive. Usually this is not the case. In the real world, the dependent variable depends on more than one variables. For example, your midterm marks depends on how much you study, how well you study, and your intelligence, etc. Many factors are there that affects your midterm marks, your exam marks. Okay, so your marks is a function of more than one variables, and therefore whenever it comes a function of more than one variable, we have partial differentiation. We have defined differentiation in mainly two types, that ordinary differentiation and partial differentiation. When a function is of only single independent variable, it is the derivative of the function with respect to the independent variable is known as the ordinary differentiation. And in case of a function of more than one variable, that is also called multivariable functions. It is the function is depending on each variable. That is, suppose you have n independent variables x1, x2 up to xn, then the function depends on partially on xn, x1, partially on x2, partially on x3, up to partially on xn. So the rate of change of the function, which is function of n independent variables, that partially depends on each of the independent variables, and that's why the rate of change of the function with respect to each of these independent variable we have to check, and it is known as partial differentiation. Other examples for multivariable examples are, first example, demand. Demand is function of price of good, price of substitutes, income, price of complements. Another real world example of a multivariable function is consumption. Consumption can be considered as function of income, taste, wages. So as income, taste and wages vary, the consumption of a product also varies. Next is graduation rates, that school quality and student quality both affect the graduation rates, and so graduation rate is a function of these two variables. So the rate of change can be considered with respect to school quality, the rate of change of graduation rates with respect to school quality, and the rate of change of graduation rates with respect to student quality. We have to consider the both. Next is birthday present satisfaction. So a function, if you consider birthday present satisfaction a function, then it depends on cost, timing, knowledge of a person that whom you are going to present the gift, and presence of card, age of that person who has the birthday on that, and you are going to give his or her some gift, etc. So the partial derivative now. It is often impossible to analyze one variable's impact if all variables are changing. In case of a function of more than one variable, if you observe only one independent variable varying, and you cannot measure the rate of change of on the dependent variable depending only that single variable. You have to consider all independent variables changing and the rate of change of the dependent variable with respect to all these independent variables separately, and these are called partial derivatives. So instead we analyze one variable's impact assuming all other variables remain constant. So how to proceed, how to check the rate of change of an independent variable with respect to one of the independent variable. How to check the rate of change in dependent variable with respect to one of the independent variables. For example, z is a function of two independent variables x and y. So this states that if you want to check the rate of change of z with respect to x variable, then keep y constant, fix the y variable, and at that time you can see the rate of change of z with respect to x variable, and that is explained in next slides. We do this through the partial derivative. If f is a function of two variables, its partial derivatives are the functions fx and fy. So partial derivative of f with respect to x, it is denoted by f with suffix x, and similarly partial derivative of f with respect to y is denoted by f with suffix y, and they are defined by fx xy. So partial derivative of f with respect to one of the independent variable x is defined as limit. In terms of limit, it is limit h tends to 0 f of x plus h comma y minus f of xy by h. So if you see here, the change is only in x direction, or the change is only in x variable. The definition says that the y variable is fixed. Similarly, when it is partial derivative of f with respect to second independent variable y, at that time the x variable is fixed and the rate of change is checked with respect to the change in y variable only. So this is definition, this is a classical definition of partial derivatives of function f of two independent variables x and y. Now notation for partial derivatives. Before we go to partial differentiation, we introduce this. If z is a function of two independent variables x and y, we write f with suffix x xy, or f with suffix x just, or it is also denoted by del f by del x. In case of the ordinary derivative, the derivative of function fx with respect to the x variable was df by dx. Here there is a slight change in the notation because there is a partial derivative del f by del x is used. Del by del x means the operator, when we operate del by del x on some function of x or more than one variable containing one of the variable as x, then del by del x means partial derivative with respect to x, like d by dx represents ordinary derivative with respect to x. So del by del x of f, or del f by del x, or if z is equal to f of xy, we consider it is also written del z by del x, or f1, because first variable we have considered as x and second variable as y. So f1 means partial derivative with respect to first independent variable x, or capital D with suffix 1 f, that is first partial derivative of f with respect to the first variable, or dxf. All these are the same. These are different notations different authors or teacher used. Similarly, notation with for the first order partial derivative with respect to the independent variable y. Y is considered here as second independent variable, so 2 suffix is used, or y itself is used for partial derivative with respect to y. Now, rules for finding partial derivatives of a function z, which is function f, which is represented by f of xy. For example, z equal to x square plus y square, z equal to sine of x plus y, z equal to e raised to xy. So to find fx means del f by del x, or partial derivative of the function z or f with respect to x, regard y as a constant. So at that time consider y as a fixed variable, constant means constant, and differentiate the function f of xy with respect to x. So if you have a function x square plus y square, then its partial derivative with respect to x will be derivative of first term x square is 2x, and derivative of y square will be partially with respect to x will be 0 because y is treated as constant when we differentiate partially with respect to the x variable. Similarly, to find fy, regard x as constant and differentiate f of xy with respect to y. Here the rules for differentiation are the same which are used for ordinary differentiation. The partial derivatives of f at point AB are the slopes of the tangents c1 and c2 as shown in the figure. Now this is important. Before you see the figure, first we consider y is equal to f of x, means y is dependent variable and x is independent variable. So y equal to f of x, or a function f of xy equal to constant, where y is considered depending on x. So x is only independent variable. In this case, in one variable calculus, if you have observed, any function y equal to fx or fxy equal to c represents a curve in xy plane. And when you find derivative of the function fx with respect to x, that is dy by dx, that gives you the expression for the slope. So if you find dy by dx at any point AB of the which is on any point AB which is on the curve y equal to fx, then the value of dy by dx at any point AB is nothing but the slope of the tangent drawn to the curve y equal to f of x at the point AB. So any function of one independent variable represents a curve in plane. Now when we consider a function of more than one variable, particularly we are considering a function of two independent variables. So when we consider a function of two independent variables, say x and y, then z is depending on them, then z is a function of x and y. So if we consider a function, for example, z is equal to square root of 1 minus x square minus y square, that is, this equation is nothing but x square plus y square plus z square equal to 1. So this is actually equation of the unit sphere, having unit sphere, so radius is 1 and center is origin. So considering z as a function of x and y with this expression z equal to square root of 1 minus x square minus y square, we can have partial derivatives of z with respect to x and y, and these partial derivatives gives us nothing but slope of tangent drawn to some curve. Now what is that curve? Let us see that. That is these curves are c1 and c2. So in this figure there are x, y, z axis. Now the blue surface is there. So I wanted to say that a function of one independent variable represents a curve in xy plane, and a function of two independent variables represents a surface in the space R3. Okay, so curve is embedded in R2, and a function of the kind z equal to f of xy is a surface embedded in R3. So here S is a surface which have equation like z equal to f of xy. Now when you find the partial derivative of z or f given here with respect to x, at that time we keep y constant. So suppose we consider y equal to 1, okay, we have to give a fixed value of y also. So in this figure there is a point P ABC on the surface S. So C is the value when you put x equal to a and y equal to b in the equation of the given surface, you get z equal to c. So that indicates that a comma b comma c, that is denoted by capital P, it is a point on this surface S. So S is surface having equation z equal to f of xy. P is a point on this surface having coordinates a comma b comma c. Then the partial derivative of this function z equal to f of xy, for which geometrically it is a surface S as shown in the figure, its partial derivative with respect to x is nothing but it is the slope of the tangent drawn to the curve C1. Why C1? Because it is the curve, consider the curve that is intersection of the plane y equal to b, that is y equal to constant, and here we are checking the partial derivative at point a comma b comma c, and we are finding the partial derivative at point a b c where y coordinate is b. So we consider the intersection of the surface with the plane y equal to b. Now the plane y equal to b will cut the surface, and the intersection point of the plane y equal to b and the surface y equal to f of xy, it is a curve say c1, and the partial derivative del f by del x at point ABC will be a real number, and that will give us the slope of the tangent drawn to this curve at point ABC, and this tangent should be in the plane in which the curve is there, means in the plane y equal to constant. Similarly, partial derivative with respect to y variable means find intersection of the given surface, that is represented by z equal to f of xy and x equal to a, that surface, that plane, and the curve, the point a comma b comma c is on that curve, it is also on the surface, and so the slope of the tangent to the curve of intersection of x equal to a and the surface z equal to f of xy, it is given by del f by del y. So for particular paraboloid, this example is discussed, z equal to 4 minus x square minus 2y square, that is a paraboloid, and here C1, it is a curve that is obtained by the intersection of the plane y equal to 1 with the surface z equal to 4 minus x square minus 2y square, and the slope of the tangent at point 1 comma 1 comma 1, it is nothing but the partial derivative of z with respect to x at point 1 comma 1 comma 1. Similarly, the partial derivative of the function z, that is del z by del y, is nothing but the partial derivative of 4 minus x square minus 2y square with respect to the y variable, and it is nothing but the slope of the tangent drawn to at the point 1 1 1, and this 1 1 1 point is considered on the curve C2, which is intersection of the surface z equal to 4 minus x square minus 2y square and the plane x equal to 1. Now the notations for second order partial derivatives.